There are places on this planet where logic should say stop, where wind tears at steel, oceans swallow foundations, and gravity itself feels like an enemy. Yet humanity doesn't step back, it builds. Across deserts, oceans, frozen tundras, and crowded megacities, colossal structures rise where survival alone is difficult, let alone construction. These aren't ordinary buildings or bridges. They are experiments pushed to the edge of physics. Projects so complex and risky that even seasoned engineers pause in disbelief. Some stretch across miles of open water. Some pierce the sky beyond the clouds. Others harness forces powerful enough to reshape landscapes or control entire rivers. Today, you're not just watching architecture. You're witnessing ambition at its most extreme. Join us as we explore impossible megaprojects, the most dangerous constructions on Earth, and uncover how human ingenuity turns the unbuildable into reality. Clinging to a sheer cliff face inside the towering sandstone pillars of Zhangjiajie National Forest Park, a transparent structure rises like something from science fiction. This is the Bailong Elevator, the 100 Dragons Elevator, a vertical transport system built where nature never intended machinery to exist. Completed in 2002, it holds the title of the world's tallest outdoor glass elevator, climbing roughly 326 meters along the face of a quartz sandstone cliff. Instead of a winding mountain trek that once took hours, visitors now ascend in under 2 minutes, suspended between sky and rock with nothing but glass separating them from the abyss. Engineering here wasn't about height alone, it was about survival against terrain. Massive steel anchors were drilled deep into the cliff to stabilize the structure, while vibration and load distribution had to be carefully managed to protect both passengers and the fragile geological formations surrounding it. The elevator operates in 3 double-deck cabins, capable of carrying thousands of passengers per hour, a logistical necessity in one of China's busiest scenic parks. Designers had to account for high winds, humidity, temperature shifts, and the seismic sensitivity of the region, all while ensuring the structure blended visually into a protected natural landscape. But beyond engineering numbers, the experience defines it. As the cabin glides upward, forests shrink beneath your feet and stone towers rise around you, a perspective that transforms transportation into spectacle. The Bailong Elevator isn't just infrastructure. It's humanity inserting precision engineering into a vertical wilderness, redefining access to landscapes once reserved only for the most determined climbers. In a country where large portions of land sit below sea level, survival itself depends on engineering. Rising from the coast of the Netherlands is a system so vast, it's often called one of the greatest civil engineering achievements of the modern era, the Delta Works. This isn't a single dam or barrier. It's an interconnected network of dikes, sluices, locks, levees, and movable storm surge barriers, built after the catastrophic 1953 North Sea flood that killed more than 1,800 people and devastated thousands of homes. The message was clear: either control the sea or live at its mercy. Spanning decades of construction beginning in the late 1950s, the project dramatically reshaped the Dutch coastline by closing off estuaries and reinforcing vulnerable regions. Engineers shortened the exposed coastline by hundreds of kilometers, reducing flood risk and protecting millions of residents and vast economic infrastructure. The crown jewel is the Oosterscheldekering, a massive movable barrier stretching about 9 kilometers. Instead of sealing the sea permanently, giant steel gates remain open under normal conditions to preserve ecosystems of fisheries, but during storms they descend, holding back surging tides with staggering force. Designing structures like this meant confronting extreme variables: tidal energy, saltwater corrosion, shifting seabeds, and waves powerful enough to destroy conventional defenses. Every component required precision, from reinforced concrete piers to hydraulic systems capable of moving gates weighing hundreds of tons. Today, the Delta works stand not just as infrastructure, but as a national shield, a reminder that geography is not always destiny. Through ingenuity and persistence, the Dutch didn't retreat from rising waters. They engineered a way to coexist with them. It's proof that sometimes the greatest construction challenge isn't reaching the sky, but holding back the ocean itself. Cut deep into the rugged canyon of the Colorado River stands a structure that redefined what modern engineering could accomplish. The Hoover Dam isn't just a wall of concrete. It's a symbol of ambition built during one of the harshest economic periods in modern history. Completed in 1936, this colossal arch-gravity dam rises about 221 meters high and stretches 379 meters across Black Canyon, straddling the border between Arizona and Nevada. Its purpose was monumental: tame the unpredictable Colorado River, provide irrigation water, control floods, and generate electricity for a rapidly growing region. The construction challenge was staggering. Workers first diverted the river through massive tunnels carved in the canyon walls. Then came the concrete. More than 4.4 million cubic meters poured in carefully planned blocks rather than one single mass. If cast all at once, the heat from curing could have taken over a century to dissipate and crack the structure apart. To solve this, engineers embedded hundreds of miles of cooling pipes throughout the concrete. Chilled water circulated through them, accelerating cooling so each block solidified safely in weeks instead of decades. A technique that became a model for future megaprojects. Behind the dam lies Lake Mead, one of the largest reservoirs in the United States, storing tens of billions of cubic meters of water and supplying hydroelectric power to millions across the Southwest. Beyond statistics, Hoover Dam represents control over scale, harnessing natural forces powerful enough to carve canyons and redirecting them toward human needs. Even nearly a century later, engineers still study it, not just for its size, but for the ingenuity that made its construction possible. Hoover Dam proves that sometimes the greatest engineering triumphs aren't about reaching upward, but about mastering the forces flowing beneath our feet. Out in the turquoise waters of the Persian Gulf lies a project so ambitious it can be seen from space. A man-made island shaped like a giant palm tree. This is Palm Jumeirah, one of the boldest land reclamation experiments ever attempted. Constructed in the early 2000s, the island wasn't built with steel or concrete foundations, but primarily with sand and rock. Engineers dredged roughly 120 million cubic meters of sand from the seabed and reinforced it with about 7 million tons of rock to form the crescent breakwater, protecting the palm from waves and erosion. That's material on a scale comparable to building several pyramids. Creating the iconic shape required extraordinary precision. Instead of traditional surveying alone, teams relied heavily on satellite-based positioning systems to guide dredging vessels, ensuring the fronds and trunk aligned exactly with the master plan. Without accurate placement, the entire structure could have warped or destabilized. But shaping the island was only half the challenge. Sand alone shifts over time, so engineers used vibrocompaction, vibrating probes inserted deep into the seabed to densify and stabilize the ground. This process reduced settlement risk and made it possible to support hotels, roads, and luxury residences above. Today, Palm Jumeirah hosts thousands of homes, resorts, and infrastructure networks. Yet beneath the glamour lies a continuous battle against nature. sediment movement, coastal erosion, and environmental impacts that require ongoing monitoring and maintenance. Palm Jumeirah isn't just an island. It's a statement, proof that modern engineering can redraw coastlines, reshape geography, and turn imagination into physical reality on a planetary scale. Stretching across one of the most unpredictable bodies of water in East Asia, the Hangzhou Bay Bridge is less a road and more a test of engineering nerve. This massive highway crossing links the cities of Jiaxing and Ningbo along China's eastern coast. At about 35.7 kilometers long, it ranks among the longest transoceanic bridges ever built. And its purpose wasn't just convenience. By carving a direct path over the bay, it slashed travel distance between Ningbo and Shanghai from roughly 400 kilometers to 180 kilometers, cutting journey time nearly in half. But the numbers alone don't capture why engineers call this project extreme. Hangzhou Bay is infamous for violent tidal forces, typhoon-driven winds, seismic risk, and waves that can climb several meters high. Designing a stable structure here meant confronting multiple natural stresses simultaneously: currents, corrosion, wind loading, and shifting seabeds. Instead of relying on traditional concrete piles, engineers drove deep steel piles into the seabed, chosen specifically for durability against corrosion and tidal stress. Massive cranes weighing thousands of tons positioned bridge sections into place under brutal working conditions at sea. Even the structural form was deliberate, a cable-stayed configuration capable of resisting complex loads while maintaining flexibility under extreme environmental forces. The result is a structure where load paths, material selection, and geometry all serve a single goal: survival. Because in a location like this, failure isn't theoretical. It's calculated against every tide, every storm, and every vibration transmitted through steel anchored beneath the ocean floor. And yet, day after day, vehicles glide across it without a second thought. Proof that sometimes the most dangerous constructions don't look dangerous at all. Clinging to the face of a sheer cliff as if gravity were optional, the Hanging Temple is one of the most improbable structures ever built by human hands. Located near the base of Mount Hung in Datong, this architectural anomaly dates back more than 1,500 years, with origins traced to the late Northern Wei Dynasty, period around the 5th century. At first glance, it looks impossible, a cluster of wooden halls and walkways suspended about 75 meters above the ground, embedded into vertical rock. But what appears fragile is actually calculated engineering. The temple isn't simply hanging from those thin-looking stilts beneath it. Those supports are partly psychological, visual reassurance. The real load-bearing system lies hidden. Horizontal wooden beams anchored deep into holes carved into the cliff face. The rock itself carries much of the weight, distributing forces inward rather than downward. In placing the temple, there wasn't just aesthetic ambition. The elevation protects it from flooding and erosion. The overhanging cliff shields it from rain and direct sunlight, natural climate control that has helped preserve the structure for centuries. Positioning also reduced wind exposure compared to ridgetop construction. But engineering is only half the story. Inside, the temple uniquely blends Buddhism, Taoism, and Confucianism, three philosophical traditions typically housed separately. It's one of the rare physical spaces where these belief systems coexist architecturally, symbolizing coexistence rather than competition. Still, survival has never been guaranteed. Weathering, seismic activity, and centuries of human use constantly threaten structural integrity. Modern restorations reinforce weakened beams, yet the core design, timber inserted into stone, remains fundamentally ancient. And that's what makes the Hanging Temple unsettling. It's not just that it stands on a cliff. is that it has stood there for over a millennium, balancing faith, physics, and risk, quietly daring gravity to disagree. Rising from its own artificial island, like a sail frozen in motion, the Burj Al Arab stands as one of the most daring symbols of modern engineering and architectural ambition. Positioned just off the coast of Dubai, this structure was never meant to simply exist on land. From the very beginning, it challenged geography itself by being built where no natural foundation was available. Instead of solid ground, engineers faced loose, shifting seabed sand. To make construction possible, hundreds of massive concrete piles were driven deep into the seabed, relying on friction rather than bedrock for stability. This approach demanded precise calculations, because even small errors could have led to uneven settlement or long-term structural instability. The artificial island beneath the tower acts as both a foundation and a buffer, absorbing wave energy from the Arabian Gulf. The building's iconic sail-shaped form is not just a visual statement. Its exterior skin is made from a lightweight, Teflon-coated fiberglass fabric stretched over a steel framework. This material choice reduces wind pressure on the structure while reflecting intense sunlight, an essential adaptation in Dubai's extreme climate. At night, the same surface becomes a glowing canvas, transforming the tower into a landmark visible for kilometers. Inside, the Burj Al Arab emphasizes vertical scale and theatrical space. The central atrium rises dramatically through most of the building's height, creating an interior volume rarely attempted in hospitality architecture. Every accommodation is a duplex suite, reinforcing the building's identity as a symbol of exclusivity rather than efficiency. Even features like the rooftop helipad serve dual purposes, functioning both as infrastructure and as global media spectacle. Yet beneath the luxury lies constant engineering tension. Salt-laden air accelerates corrosion. High humidity stresses materials, and extreme temperature swings cause continual expansion and contraction. Unlike inland skyscrapers, coastal structures require relentless monitoring and maintenance to remain safe and functional. The Burj Al Arab's elegance is therefore sustained not by permanence, but by continuous human intervention. This is what makes the structure truly extraordinary. The Burj Al Arab is not simply a hotel built on water. It is a demonstration of how modern engineering can manufacture stability, prestige, and permanence in an environment that naturally resists all three. Carving a path through the narrowest point of Central America, the Panama Canal stands as one of the most audacious feats of human engineering in history. Connecting the Atlantic and Pacific Oceans, it transformed global trade by drastically shortening maritime routes, eliminating the need for ships to navigate the treacherous waters around South America's Cape Horn. The canal was never just a waterway. It was a battle against geology, climate, and disease. Construction required moving millions of cubic meters of earth through tropical jungles and mountainous terrain. Workers contended with heavy rainfall, unstable soils, and relentless tropical diseases such as malaria and yellow fever. The early 20th century technology available made excavation stabilization, and water management extraordinarily challenging. Yet engineers overcame these obstacles with ingenuity, inventing lock systems that could lift ships hundreds of feet above sea level and then safely lower them to the next waterway. The canal's locks are marvels of precision engineering. Massive gates, some as tall as an 11-story building, operate with minimal friction, moving enormous ships in a matter of minutes. To conserve fresh water, regulating basins adjacent to each lock recycle water for the next cycle, an innovation that allows the canal to function efficiently despite its tropical environment. The system is so finely tuned that a single misalignment or mechanical failure could bring global shipping to a halt. Over a century after its completion, the Panama Canal continues to astonish engineers and travelers alike. Modern expansions have accommodated the largest vessels on Earth, demonstrating the foresight of its original designers. Every ship passing through this waterway is a testament not just to human ambition, but to the precise orchestration of geology, hydraulics, and labor. The Panama Canal proves that when humanity confronts natural obstacles on a monumental scale, determination and engineering can bend the landscape to our will. Rising proudly above the skyline of Kuala Lumpur, the Merdeka 118 is not just a building. It is a statement of ambition and engineering audacity. At over 644 meters tall, it is the tallest building in Malaysia and the second tallest in the world, piercing clouds and redefining what is possible in urban vertical design. Its sleek, tapering form is inspired by the national motif of the hibiscus flower, blending cultural symbolism with cutting-edge engineering. Constructing a structure of this magnitude presented extraordinary challenges. Wind forces at extreme heights can twist and sway even the most rigid towers. So engineers designed a high-strength reinforced concrete core surrounded by an outer frame of steel and composite materials to provide stiffness and resilience. The foundation alone required thousands of piles driven deep into the ground, anchoring the tower securely on Malaysia's soft soil while mitigating the risk of settlement or tilting. The building's facade is equally impressive. Reflective glass and aluminum panels reduce heat gain in the tropical climate, while giving the tower a luminous, futuristic appearance. Inside, double-deck elevators travel at blistering speeds to service offices, observation decks, and luxury residences, while mechanical systems are meticulously engineered to handle the immense vertical distance and density of occupants. Merdeka 118 is more than a skyscraper. It is a vertical city, a triumph of design, construction, and ambition. Standing above Kuala Lumpur, it reminds the world that modern engineering can not only reach for the sky, but also embed cultural identity into the tallest structures on Earth. It is a testament to human ingenuity and the audacity to build where the limits of possibility meet the clouds. Towering over the turbulent waters of the Yenisei River, the Shushenskaya Dam is a monument to human ambition and industrial scale. As the largest power plant in Russia and one of the most powerful hydroelectric facilities on Earth, it generates nearly 6,400 megawatts of electricity, enough to supply millions of homes across Siberia. Its sheer size and capacity are staggering. But what makes it truly remarkable is the extreme environment in which it was built. Located deep in the Siberian wilderness, engineers had to contend with icy temperatures, strong currents, and a remote location that made transporting materials and equipment a logistical nightmare. The dam itself is a gravity arch structure designed to redirect and contain the river's immense force while withstanding both seasonal flooding and seismic activity. Every cubic meter of concrete, every steel reinforcement, had to be precisely calculated to endure pressures that would crush lesser constructions. The facility's turbines and generators are feats of mechanical ingenuity, designed to operate under continuous load while remaining accessible for maintenance in one of the harshest climates on the planet. In 2009, a catastrophic accident caused massive flooding within the dam, highlighting the extreme risks associated with controlling such colossal natural forces and underscoring the ongoing vigilance required to maintain the structure safely. The Shushenskaya Dam is more than a hydroelectric station. It is a demonstration of how engineering can harness the raw power of nature at scales almost beyond comprehension. Rising from a Siberian landscape, it embodies both the promise and peril of human ambition. A stark reminder that controlling nature demands respect, precision, and ingenuity. Rising like futuristic trees from the heart of Singapore's urban landscape, the Super Tree Grove, within the Gardens by the Bay, is more than a park. It is a bold experiment in merging nature with cutting-edge engineering. These towering vertical gardens, some reaching up to 50 meters in height, are designed to mimic the ecological functions of real trees, harnessing solar energy, collecting rainwater, and supporting a living skin of thousands of plants from around the world. Connected by the elevated OCBC Skyway, a suspended walkway winding through the tops of the super trees, visitors experience the city from an entirely new perspective. Constructing these massive structures required engineers to balance form with function. The steel frames had to support both the weight of the plants and the dynamic load of thousands of visitors, all while withstanding tropical storms and intense heat. Innovative irrigation systems and smart sensors ensure each vertical garden thrives, combining aesthetics with sustainability in a single seamless design. At night, the super trees transform into a spectacle of light and sound, creating a garden rhapsody that illuminates the park while showcasing Singapore's commitment to blending ecological consciousness with architectural daring. The sky park atop these structures is more than a vantage point. It is a symbol of what human creativity can achieve when imagination and engineering intersect. The Super Tree Grove proves that construction doesn't always have to defy gravity in the traditional sense. Sometimes, the most impressive engineering feats are those that elevate life itself, turning a park into a living, breathing, and glowing urban monument. Cutting across the Japanese landscape at speeds that once seemed impossible, the Shinkansen redefines what it means to move people efficiently and safely. First introduced in 1964, the Shinkansen was not just a train. It was a statement of technological ambition, linking cities at unprecedented velocities while maintaining an extraordinary record of safety and punctuality. Traveling over 300 kilometers per hour, it slices through mountains, rivers, and urban centers with a precision that leaves spectators in awe. Constructing this high-speed network required overcoming Japan's complex geography, prone to earthquakes, typhoons, and dense urban sprawl. Engineers developed earthquake-resistant tracks, elevated viaducts, and meticulously leveled tunnels to allow trains to glide smoothly even under extreme conditions. The trains themselves employ aerodynamic designs that minimize noise, reduce energy consumption, and ensure passenger comfort at velocities that would challenge ordinary rail vehicles. Beyond technology, the Shinkansen symbolizes Japan's vision of modernity and connectivity. Stations are carefully integrated into city planning, allowing seamless transitions between local transit and high-speed routes. Suspended high above the forests of the Czech Republic, the Sky Bridge 721 is not just a crossing. It is an adrenaline-fueled experience that challenges both perception and engineering. Stretching an astonishing 721 meters, it claims the title of the longest pedestrian suspension bridge in the world, hovering over deep valleys and rolling hills where even the strongest gusts can make the structure sway. Constructing a bridge of this scale required meticulous planning. Engineers had to balance extreme length with minimal weight, ensuring the steel cables, tension anchors, and deck could withstand not only the weight of visitors, but also the relentless wind currents that sweep through the mountains. The bridge is anchored into solid rock, but even so, its slight movement is intentional, creating a sensation of walking on air while maintaining structural integrity. Access points are carefully integrated with the surrounding landscape, allowing hikers and thrill seekers to ascend safely to the suspension start. The deck itself combines lightweight materials with reinforced steel to provide stability without sacrificing transparency or the feeling of openness. At night, subtle lighting transforms the bridge into a glowing ribbon across the valley, highlighting its engineering brilliance and the natural beauty below. Sky Bridge 721 is more than a walkway. It is a daring statement of human creativity and precision. It turns what could be an ordinary observation into a visceral encounter with height, wind, and perspective. A reminder that the most breathtaking constructions often exist at the edge of fear and engineering mastery. Stretching gracefully across the Gardon River in southern France, the Pont du Gard stands as a testament to the ingenuity of ancient engineers. Built nearly 2,000 years ago by the Romans, this three-tiered stone aqueduct was designed to carry water over 50 kilometers from springs near Uzes to the city of Nîmes, supplying a growing population with a reliable source of life. Its elegance is matched only by its precision. The gradient is so slight, roughly 34 centimeters per kilometer, that water flowed steadily without modern pumps. Constructing Pont du Gard demanded mastery of geometry, materials, and human labor. Massive limestone blocks were quarried and carefully shaped, then lifted into place without the aid of cranes or machinery. Each arch had to distribute weight evenly, allowing the structure to withstand both the river's seasonal floods and the centuries of erosion that would eventually challenge it. The engineers' understanding of load, tension, and balance ensured the aqueduct could endure in a landscape prone to shifting soils and heavy rainfall. Beyond its function, Pont du Gard is a cultural and architectural marvel. Its harmonious proportions and monumental scale convey not only utility, but also the Romans' vision of permanence and civic pride. Walking across it today, visitors experience both the engineering genius of antiquity and the aesthetic sophistication that made the aqueduct more than a conduit. It became a symbol of civilization itself. Pont du Gard proves that some of humanity's most impressive constructions are not only about power or height, but about precision, foresight, and the ability to turn necessity into enduring beauty. Perched on the edge of Norway's Geirangerfjord, the wave, Bulgen, rises like a frozen tidal wave, daring gravity to defy it. This residential structure is as dramatic as the natural landscape around it, its sweeping, undulating facade mirroring the fjord's glacial curves while testing the limits of modern architecture. Every floor follows a precise curvature, creating apartments with spectacular views, but challenging engineers with complex load distribution and cantilevered sections that extend over the cliffside. Construction required meticulous planning and innovative engineering. Reinforced concrete and high-strength steel were used to support the building's overhanging forms, while each apartment had to be aligned perfectly to maintain both structural integrity and the intended aesthetic. The site itself presented additional hazards: steep slopes, potential landslides, and harsh Nordic weather, which meant that foundation work and material handling had to account for both safety and long-term durability. But the wave is more than an engineering challenge. It is a marriage of nature and human creativity. Its design transforms a residential complex into a sculptural landmark, proving that functional living spaces can also be monumental works of art. Walking along its terraces, one cannot help but feel the tension between permanence and the raw, dynamic forces of nature surrounding it. The wave, Bulgen, is a statement that architecture can do more than occupy space. It can mimic nature, challenge expectations, and transform the edge of a fjord into a symbol of audacious human vision. Rising along the Reykjavik waterfront, the Harpakonserhall is a stunning fusion of art, architecture, and engineering. Its crystalline facade, composed of hundreds of geometric glass panels, reflects sunlight in the northern sky, creating a kaleidoscope of colors that changes with every hour and weather condition. The building was designed not only to host world-class performances, but also to integrate seamlessly with Iceland's dramatic natural environment, blending the urban shoreline with the volcanic landscape beyond. Constructing Harpa demanded precision and innovation. The unique glass panels were custom-engineered, requiring exact calculations for thermal expansion, wind loads, and light refraction. Behind the seemingly delicate exterior lies a robust steel frame capable of supporting multiple performance halls and exhibition spaces, while withstanding Reykjavik's harsh coastal winds and cold temperatures. The building also incorporates advanced acoustic engineering, ensuring that each concert, from symphony to contemporary performance, reaches audiences with perfect clarity and resonance. Harpa is more than a functional space. It is a living piece of art. At night, the facade illuminates with dynamic LED displays, turning the hall into a glowing beacon visible across the harbor. The combination of structural ingenuity, aesthetic brilliance, and cultural purpose makes it a landmark that embodies Iceland's commitment to creativity, innovation, and the fusion of human artistry with environmental context. Reaching skyward with ambitions that stretch beyond Earth itself, the Starship is not just a rocket. It is humanity's next step toward interplanetary travel. Designed by SpaceX, Starship aims to carry dozens of passengers and tons of cargo to destinations ranging from low Earth orbit to Mars. Standing at 120 meters tall, when stacked with its booster, it dwarfs nearly every rocket that came before, a gleaming symbol of audacious engineering and technological innovation. Building Starship presented challenges unlike any conventional construction project. The stainless steel exterior must withstand extreme temperatures during atmospheric reentry, while the rocket's engines generate immense thrust that test the limits of material strength and precision engineering. Every weld, every plate, every joint is engineered to tolerate repeated launches and landings, transforming what was once disposable aerospace hardware into a reusable spacecraft capable of multiple missions. Rising dramatically above the historic skyline of St. Petersburg, Lochta Center. The Lochta Center is not just the tallest building in Russia. At 462 meters, it is the tallest in all of Europe, but a towering testament to human ambition and engineering mastery. From afar, its twisting spire appears to spiral into the heavens, a frozen flame of steel and glass reflecting the shifting northern light. The sleek, aerodynamic design is not purely for visual drama. It is a carefully calculated solution to reduce wind pressure on the tower, ensuring stability against fierce gusts and extreme weather, a necessity in the Gulf of Finland's harsh climate. Each pane of its ultra-clear glass facade was meticulously engineered to balance transparency, thermal efficiency, and resilience against ice and snow, creating a shimmering exterior that both complements and dominates the surrounding cityscape. Constructing the Lochta Center was a feat of ingenuity that challenged the boundaries of modern engineering. The tower rests on a complex foundation of deep piles driven into soft and uneven soils near the bay, with precise load distribution to prevent long-term settlement. The reinforced concrete core, coupled with a high-strength steel frame, supports the twisting structure while allowing it to sway slightly under wind stress. A subtle movement designed to prevent damage rather than compromise stability. High-speed elevators, intelligent HVAC systems, and advanced safety mechanisms transform the skyscraper into a self-contained vertical city, with office spaces, observation decks, and public areas integrated seamlessly into one structure. The tower's spiral form is more than aesthetic elegance. It is an engineering strategy. By gradually rotating as it ascends, the design reduces wind vortex effects that could otherwise exert immense lateral forces, allowing the Lochta Center to stand tall and unshaken where a conventional vertical tower might falter. At night, the spire glows like a beacon, visible from kilometers away, turning the building into a landmark and a symbol of St. Petersburg's modern era while paying homage to its rich architectural heritage. Lac du Center is not just a skyscraper. It is a bold statement about human capability. It demonstrates how careful planning, innovative materials, and visionary design can overcome environmental and geological challenges to create a structure that is simultaneously functional, sustainable, and visually stunning. Standing beneath its soaring spire, visitors and engineers alike feel both awe and inspiration, reminded that with ambition, precision, and creativity, humanity can reach heights that were once unimaginable, crafting a marvel that will dominate the skyline for generations to come. Rising from the windswept plains of southern England, Stonehenge is a structure that continues to mystify scholars, engineers, and visitors alike. Built over 4,000 years ago, its massive sarsen stones, some weighing up to 30 tons, were transported from quarries miles away, a feat that would challenge even modern machinery if attempted without cranes or trucks. The purpose of Stonehenge remains a subject of debate, but the precision with which its stones were arranged, aligned with solstices and celestial events, suggests a sophisticated understanding of astronomy and geometry far ahead of its time. Constructing Stonehenge demanded incredible ingenuity. Ancient builders used wooden sledges, ropes, and sheer manpower to move and raise the stones into place, creating post and lintel formations that have survived millennia. The foundation and placement were calculated carefully to ensure stability, even as the site endured centuries of erosion, shifting soil, and weather extremes. The engineers of that era managed to create a structure that is both monumental and enduring, despite the complete absence of modern technology. Stonehenge is more than a prehistoric curiosity. It is a testament to human ambition and organizational skill. Its precise alignment with the sun, its harmonious proportions, and the sheer scale of the undertaking make it a marvel of ancient engineering. Standing among the stones today, one feels the weight of history and the audacity of those who dared to construct something that could withstand both time and nature, leaving a legacy that continues to inspire awe and wonder.
The Three Gorges Dam stretches across the Yangtze River with commanding presence, immediately conveying monumental scale and human ambition as mountains and water merge with engineering mastery. Its massive concrete walls and stepped spillways rise against the river's flow, creating a landscape transformed by design and determination. Spanning over 2 kilometers and standing more than 180 meters tall, the dam integrates hydroelectric turbines, navigational locks, and flood control systems, forming the world's largest power-generating facility by installed capacity. Each component reflects advanced structural engineering, precise calculations, and decades of coordinated construction efforts completed in the early 21st century. The project reshaped the region's geography, enabling renewable energy production, controlling seasonal floods, and improving navigation for inland shipping. At the same time, it required large-scale relocation of communities and careful management of ecological impact, demonstrating the complex balance between human progress and environmental stewardship. Standing on observation platforms above the surging waters, visitors feel both awe and introspection, sensing the immense power of flowing rivers harnessed by human ingenuity, and understanding how engineering can transform nature while leaving an indelible mark on civilization.
Perched high above the city of Cusco in Peru, Sacsayhuaman is a fortress that continues to baffle historians and engineers alike. Constructed by the Inca around the 15th century, its massive stone walls are made of gigantic, irregularly shaped blocks, some weighing over 100 tons, perfectly fitted together without mortar. The precision of the stonework is so exact that even a razor blade cannot be inserted between the stones, a testament to the extraordinary skill and ingenuity of Inca engineers. Moving and assembling these monolithic stones on the steep hillsides of the Andes posed immense challenges. There were no cranes, no pulleys, no modern machinery, only ingenuity, manpower, and a deep understanding of leverage and geometry. The walls are designed to resist seismic activity, a necessity in this earthquake-prone region, with slightly inclined blocks and interlocking stones that allow the fortress to absorb shocks rather than crumble under them. Sacsayhuaman is more than a military structure. It is a symbol of Inca mastery over both material and terrain. Its terraces, ramparts, and ceremonial platforms demonstrate an understanding of space, defense, and aesthetics rarely seen in ancient construction. Standing among the massive stones today, visitors can sense the ingenuity, planning, and ambition that allowed a civilization to create something both functional and awe-inspiring, enduring for centuries despite the harsh mountain environment. Rising proudly above the skyline of New York City, Chrysler Building is more than an iconic skyscraper. It is a symbol of ambition, elegance, and the roaring spirit of the 1920s. Completed in 1930, it briefly held the title of the tallest building in the world, surpassing all expectations with its 319-meter spire that gleams in sunlight like polished metal. Its distinctive Art Deco design, with stainless steel cladding, terrace crown, and automotive-inspired gargoyles, celebrates both industrial progress and architectural artistry. Constructing the Chrysler Building was an engineering triumph. Built in an era without modern computer modeling, engineers and architects had to calculate weight distribution, wind loads, and structural integrity with remarkable precision. The steel frame supports a delicate facade of brick and metal, while the iconic spire was secretly assembled inside the building and then hoisted into place, a daring move that secured its status as the world's tallest structure at the time. Inside, the building was designed with both functionality and luxury in mind. Elevators, lighting, and office spaces were state-of-the-art for the era, while the interiors echoed the Art Deco style that made the skyscraper not just a workplace, but a work of art. Even today, the Chrysler Building continues to inspire awe for its combination of aesthetic vision and structural ingenuity, standing as a testament to a time when ambition reached for the sky, quite literally.
The Guangzhou CTF Finance Center rises like a sleek vertical needle above the Pearl River, immediately signaling modern ambition and architectural precision. Its glass and steel facade reflects sunlight by day and city lights by night, creating a shimmering icon within Guangzhou's rapidly evolving skyline. Standing at 530 meters with 111 floors, the tower accommodates offices, hotels, retail space, and observation decks. Its advanced structural design incorporates tuned mass dampers and high-performance materials to resist wind and seismic forces, while ultra-fast elevators transport occupants smoothly through the building's vertical cityscape. Completed in 2016, the project exemplifies a fusion of engineering innovation and urban planning. The tower's integration into Guangzhou's central business district reflects strategic intent to concentrate commerce, finance, and hospitality within a single landmark, reinforcing the city's position as a global economic hub. From observation platforms and panoramic interiors, visitors feel both awe and perspective, suspended above the urban expanse while witnessing human ingenuity transform concrete, steel, and glass into a monument of ambition, connectivity, and modern design.
Stretching elegantly across the Tarn Valley in southern France, Millau Viaduct is not merely a bridge. It is a monumental statement of engineering audacity and aesthetic brilliance. Completed in 2004, it holds the title of the tallest bridge in the world, with its highest mast soaring 343 meters, surpassing even the height of the Eiffel Tower. From a distance, it appears almost to float above the valley, a slender line of steel and concrete connecting two rugged cliffs while leaving the natural beauty of the landscape almost untouched. Its design harmonizes with the environment rather than dominating it, creating a visual experience as breathtaking as the engineering achievement itself. Constructing the Millau Viaduct demanded innovation on a scale rarely seen in modern civil engineering. Instead of building from the valley floor, a method that would have been impractical and environmentally intrusive, engineers assembled massive segments of the bridge deck on level ground at both ends and then used synchronized hydraulic jacks to inch the structure forward over the chasm, advancing just centimeters at a time. Each of these massive sections, weighing hundreds of tons, had to be perfectly aligned and balanced, while the cable-stayed mass absorbed both vertical loads and lateral stresses caused by wind and potential seismic activity. The steel deck, concrete pylons, and tension cables form a symphony of structural harmony, each component meticulously designed to maintain stability while giving the illusion of lightness and elegance. The Millau Viaduct is also a triumph of human foresight and logistics. Transporting materials to such a remote and rugged location required precision planning and creative problem-solving. Every crane placement, every cable installation, and every section of concrete poured had to account for the challenging winds that sweep through the valley and the tight construction timelines imposed by seasonal weather conditions. Safety and precision were paramount, as even the smallest miscalculation could have compromised the entire structure. Beyond its technical achievements, the Millau Viaduct is a cultural and aesthetic icon. Drivers crossing it experience a sense of awe and vertigo as they soar hundreds of meters above the valley floor, the surrounding mountains stretching endlessly into the horizon. Tourists, photographers, and engineering enthusiasts from around the world flock to witness not only the scale, but also the grace of this bridge, a place where functionality and beauty coexist seamlessly. It stands as a testament to the power of human ingenuity, proving that with ambition, innovation, and meticulous planning, engineers can bend the forces of gravity and nature into structures that inspire awe and endure for generations. Rising from Manhattan's west side, Hudson Yards is more than just a cluster of towers. It is a testament to modern urban ambition and architectural audacity. As the largest private real estate development in U.S. history, Hudson Yards transforms a once-overlooked stretch of the city into a vertical city within a city, blending residential, commercial, and cultural spaces into a seamless, soaring metropolis. At its heart, the development combines skyscrapers, plazas, and public art installations in a design that simultaneously dazzles the eye and pushes the limits of urban engineering. Constructing Hudson Yards required feats of precision and innovation. The entire district is built atop a complex platform above active rail yards, demanding enormous support structures and careful weight distribution to ensure safety without disrupting the busy transit lines below. Massive steel trusses, reinforced concrete slabs, and vibration dampening systems work together to maintain stability, while the towers themselves are engineered to withstand wind loads, shifting soil, and the dynamic stresses of one of the world's busiest cities. Every corner, from the glass facades to the public spaces, had to balance structural integrity with aesthetic appeal, creating a cohesive skyline that feels both futuristic and grounded. Central to the development is the vessel, an intricate honeycomb-like sculpture and observation structure that draws the eye upward and invites exploration. Its interconnecting staircases, reaching multiple levels, create a sense of vertical movement while testing the limits of cantilever construction. Meanwhile, the Edge, a sky-high observation deck, juts out from one of the towers, giving visitors the sensation of walking on air over Manhattan, a thrilling reminder of what modern engineering can achieve. piercing the skies of Dubai. Burj Khalifa is more than the tallest building in the world. It is a vertical monument to human ambition, engineering precision, and architectural audacity. Standing at a staggering 828 meters, Burj Khalifa dominates the skyline, its tapering spire reaching into the clouds and redefining the very limits of what is possible in urban construction. Every aspect of the building, from its Y-shaped floor plan to its sleek exterior cladding, is meticulously designed to optimize stability, resist extreme winds, and create an unmistakable silhouette visible from miles away. Constructing Burj Khalifa demanded ingenuity on an unprecedented scale. Engineers used a high-strength concrete core, reinforced with a buttress system of wings, to distribute the immense vertical loads while controlling sway caused by high-altitude winds. The exterior is clad in reflective glass and aluminum panels that reduce heat absorption in Dubai's harsh desert climate, while advanced mechanical and elevator systems whisk occupants across more than 160 floors with remarkable speed and safety. Each component, from structural steel to curtain walls, was precision engineered to work in perfect harmony, ensuring the tower's resilience against both environmental forces and the test of time. Beyond sheer height, Burj Khalifa is a masterclass in blending functionality with aesthetic brilliance. Its observation decks, luxury residences, corporate offices, and hospitality spaces coexist seamlessly, while the exterior's tiered design creates elegant setbacks that evoke the form of a desert flower reaching toward the sun. Engineers and architects had to overcome challenges that included foundation settlement, wind vortex shedding, and material performance under extreme temperatures, all while maintaining a visual elegance that made the building iconic. Burj Khalifa is more than a skyscraper. It is a symbol of what humanity can achieve when ambition meets innovation. It transforms the skyline of Dubai into a stage for bold engineering and creative vision, reminding the world that with determination, meticulous planning, and cutting-edge technology, we can reach heights that were once unimaginable, quite literally touching the sky.
The Fuxing high-speed train surges across China's vast landscape as a symbol of velocity, precision, and modern mobility, gliding between cities with a quiet authority that reflects the country's commitment to advanced transportation. From dense urban hubs to distant regions, its streamlined form cuts across distance, redefining how quickly people and economies connect. Operating on an expanding network of dedicated high-speed rail lines, the train reaches commercial speeds of around 350 kilometers per hour, supported by aerodynamic engineering, intelligent control systems, and reinforced track infrastructure designed for stability and safety. Its interiors balance efficiency with comfort, integrating digital monitoring, energy-optimized components, and vibration reduction technologies to sustain reliability over long distances. Introduced during the 21st century as part of a broader national rail modernization effort, the Fuxing series represents domestically developed high-speed technology aimed at improving capacity, reducing travel times, and strengthening regional integration. Continuous upgrades in materials, signaling systems, and operational coordination reflect an ongoing evolution in transport engineering. As passengers watch cities blur into countryside through panoramic windows, the experience becomes more than transit. It is a moment suspended between departure and arrival, where acceleration and stillness coexist, revealing how innovation can reshape perception of distance while carrying millions toward opportunity, connection, and motion.